Gien, France. A second presentation about redetection mobile laser scans of urban scenes based on implementation of geometric descriptors.
Okay, thank you for the introduction. So I'm presenting this paper on behalf of Fabrice Monnier, who did an internship at IGN under my supervision, and this is also a common work with Balmain Solien from IGN too. So my outline is going to be quite simple. I start with a brief introduction about tree detection, and then I'll detail the method that we have put up, and then finish with some results and the conclusion. Okay, so in introduction, why are we interested in tree detection and in urban areas? It's because trees are very important objects, so for forestry activity, of course, but also for city planning and inventory, for realistic 3D reconstruction, and for city texturation, because trees occupy a very important space in the visual landscape. And also for other applications such as autonomous navigation, visual-based localization, and automatic image tagging. So the reality work about over the past decade, vegetation detection was highly studied, but mainly based on LIDAR data, a little bit on image data too. And more than often, this data was acquired from an aerial or spatial support. There is quite few work involving textual data. For instance, Jovan and Diapopoulos work on vegetation detection from aerial images. Using usually infrared is used in this kind of works. So nowadays, with the advent of mobile mapping, we can cite Bruno that detect some vertical structures, but he did not focus really on detecting trees in urban areas. And for the other works, most of them are interested in forests and not urban areas, such as the region approach of Binet and Buch. There's also an interesting work by Pfeiffer where the tree structure is recovered by extracting cylinders. And the world of Flowerland in 2005, where geometric descriptors are extracted and tested. So what are the advantages of terrestrial data over aerial data? Well, one of the biggest advantages is that we're going to have data of much higher density, so we're going to have access to much finer details. We also have a very high accuracy because we are much closer to the object of interest. Typically, we were going to be 5 meters away of the tree that we're going to detect. So we can hope for a much more accurate vegetation detection, and we can also hope to localize the trunk in this kind of data because we are not scanning from above but from the side. The drawbacks is that the things are going to be much more complex. We're going to have visibility issues, so they're going to have to be harder to analyze, and also we're going to have huge amounts of data and performance issues. So at IGN, our mobile scanner, we call it Stealth Police, is composed of Regal lasers that are located here at the bottom of the pole here. We have several acquisition configurations, but here in our study we had a configuration where it was scanning from 0 degree to plus 70 degrees in a plane that is orthogonal to the trajectory, and so you get all the data, the self-dimension is obtained by the forward motion of the vehicle, and the vehicle itself is localized based on a combination of GPS, INS, and odometer. So this localization is very good in relative precision, so that means that when we're going to be interested in a tree, we know that we're going to have a very good geometry, but we have some low frequency shifts, especially because of GPS masks, and sometimes the vehicle can shift up to 2 or 3 meters away from the real position. So the main goal of our approach was to design a simple and generic method to detect trees in heterogeneous and complex environments in urban areas. And so the main problems we had to solve was to separate the points that correspond to the trees to the other objects that you find in urban areas. Then another problem we had was to separate individual trees within these points, and we wanted also to localize the trunks precisely. The information we have was the spatial coordinates of the points, but we also had access to the point intensity through the backscatter. And so what we did what we wanted to do was to describe the local point cloud geometry using some shape descriptors. So the first part is going to be about finding the appropriate shape descriptors to do that. Then these shape descriptors, we're going to accumulate them vertically. And finally, we're going to base our tree detection on the geometric characteristics of trunks and foliage. So now I'll detail the method itself. So it's based, the geometric descriptors are based on the work by Denontier of 2011. So in his work, he tries to separate 3 limit cases in a PCA of the neighborhood of each point. So you have 3 extreme cases, which are the point repartition can be either linear, planar, or volumetric. So to define this more precisely, so when you're going to have one eigenvalue that is much bigger than the other 2, we're going to say that the neighborhood is linear. And we're going to define a linear descriptor, defined this way, so sigma 1 minus sigma 2 over sigma 1. So it's going to be close to 1 when your neighborhood is linear, and close to 0 when it isn't. So in the same way, your planar, if your 2 first eigenvalues are much bigger than the second one, so you can define your planar descriptor that will be sigma 2 minus sigma 3 over sigma 1. Same thing, close to 0 when you're not planar, close to 1 when you're planar. And the third one is the volumetric descriptor, so all the eigenvalues have roughly the same values. And so your neighborhood is volumetric, that means that your points have a kind of random distribution in space. And we have this last descriptor, d3, that is sigma 3 over sigma 1. So these descriptors, the normalization by sigma 1 was done such that the sum of the 3 descriptors is always 1. So if you have one descriptor to 1, then the other 2 are to 0. So this makes 3 very nice extreme cases, 1, 0, 0, 0, 1, 0, and 0, 0, 1. That would be the three limit cases. So now the problem when you're doing this kind of PCA is that the result is very highly dependent on the choice of the neighborhood, and so you have to tune the neighborhood size very finely. And the very good idea in the work of Denontier was to compute this PCA and these descriptors for increasing neighborhood sizes. So you're going to try all possible sizes, or a certain limited number of possible sizes, and then for each of these sizes you compute the descriptors, and you compute the entropy of the descriptors. And if the entropy is low, it means that you're very close to one of these extreme cases that we're interested in. So we're going to select the neighborhood size that is as close as possible to one of these extreme case. That is, we're going to choose the neighborhood size for which the entropy is minimal. So this is a result for the linear descriptor. So you see you have a very good response on linear features. Also on corners, along facades, you have corners that respond pretty well. And you have a little bit of noise in the trees. Some parts of the trees are going to respond, the foliage are going to respond to this linear descriptor. For the planar descriptor, you see very high response on the flat areas on the facades, which is quite logical, and also on the trunks, because if the trunks are large enough, they're going to be considered planar, and if the trunks are small enough, they're going to be considered as linear. Okay, and the third descriptor, obviously, is going to have a good response on the trees, but you also have a good response on all the complex structures on the facade, because when you have a complex structure, you will have quite a kind of random distribution that will have a good response on volumetric descriptor. So these results are pretty good, but we have some drawbacks. For instance, the D1 descriptor will also respond on small on posts, so we will not be able to distinguish trunks from posts. But also the volumetric descriptor, as I thought, will respond on complex facade structures. So these are a few problems that we will have to solve. So to correct that, what we're going to do is to perform a probabilistic relaxation to have more regularity, in the neighborhood. Because in general, as you've seen, For instance, in the foliage, some descriptors might be a bit mixed, and we're going to try to make neighborhoods more homogeneous. So how does probabilistic relaxation work? It's an iterative process that tries to homogenize the neighborhood. So you're going to compute new probabilities at time t+1 according from the probabilities you had at the previous iteration, and you're going to update these probabilities by an increment delta p that depends on the values of the descriptors in the vicinity globally, and you weight the distance by a Gaussian so that points that are further away have less impact than points that are close by. And then we introduce a compatibility matrix that tells you what is the probability that two neighboring points have the same descriptor value, or that they have different neighboring values. So on the diagonal, you have values close to 1, because when you're planar, you have a high probability that two neighboring points are planar, for instance. And outside from the diagonal, we put lower values. And finally, based on this compatibility matrix, we can define the increments. Then we add the increment to each probability, and finally we normalize the result to get once again the probability summing up to 1. So this is the result, for instance, on the linear descriptor. This was the version before relaxation, and after relaxation, you see that the neighborhoods have been homogenized. The parts where you would have random responses, they tend to vanish. So this is the result on the planar descriptor, and this is the result on the volumetric descriptor. So you see that you get rid of most of the problems over the facade, and you get probabilities that are much more localized. So as we said, the linear descriptor tends to respond on facades, and some structures are not removed by the relaxation. In the same way, some structures, some volumetric structures over the facades are not removed by the relaxation. So even if it's a good thing because we get things that are more homogeneous, we do not solve all the problems through relaxation. The minor structures tend to vanish, but the larger structures will not get away. So to solve these remaining issues, we need to add a new descriptor, which is a cylindricity descriptor. So we're going to look if the neighborhood of the point has a shape that is close to a cylinder. Okay, so we have a new descriptor defining the probability that the point belongs to a vertical cylinder. We're mostly interested in vertical cylinders, and it's much easier to detect vertical cylinders than arbitrary cylinders, because it's going to simply be a round stack on circles in projection. Okay, so we're doing a round stack, and the number of inliers of round stack are going to tell us if the cylinder is a good approximation or not of the neighborhood. So in more details for each point, we're fitting a cylinder to the neighborhood. And the number of inliers is going to be our quality criterion, but we also need a threshold over the radius, because a plane is simply a cylinder with an infinite radius, so we need to limit the radius to be sure that we have cylinders of size that are of interest to us. That means below 1 meter, or even maybe below half a meter. If you're interested in trunks in CT, you will rarely see trunks with radius higher than a meter. And then also a line is a cylinder with 0 radius, so we also have to have a minimum radius. Okay, so this is a visualization of the cylindrical descriptors. You see it responds well on trunks and on large posts, but also it depends a little bit on facades that can present some cylindric structures. So the advantage of this descriptor is that it's going to be able to discriminate large trunks from facades, because large trunks would respond highly in the planar descriptor. So this cylindricity descriptor is going to be able to distinguish between trunks and facades. But the drawback is that some parts of the facades also have a good response in the cylindrical descriptor. And so it will not distinguish between also between trunks and the large posts. So to solve this last problem, we're going to combine all the information given by these different descriptors and perform a vertical accumulation in order to exploit the vertical redundancy that we observe in urban areas. This vertical redundancy is explained by the fact that most urban structures are vertical. May they be facades, posts, trunks, most of them are quite vertical, so by accumulation we're going to spot these kind of structures which are the ones that interest us in this work. So we're going to simply compute an accumulation map for each of the descriptors. We use the discretization step of 20 centimeters because that represents around 5 acquisition lines, so we are almost sure we will have points falling in each pixel along a structure. So this is the accumulation map for the linear, for the planar, and for the volumetric map, and this is the accumulation for the cylindric map on a test area. So what we see is that the complex structures like the windows, the balconies, flower ornaments, these things do not have a high vertical redundancy, so they tend to vanish. And what we see in the accumulation maps are the things that are vertical, which are the trunks, the posts, and the facades. The pixels the pixels that belong to the same object has to be clustered. Now that we've done this accumulation, we need to group together the pixels that belong to the same object. And we're going to do that by filtering and using a few a prioris on the expected sizes of the objects we're interested in. So to make individual objects, we're going to start by filtering by a Gaussian kernel that we're able to connect neighboring pixels which have high accumulation values. Then we do a hysteresis thresholding. That means we're going to remove the pixels with low response that will not create holes in larger objects. Then we compute we extract the connected components, and so we connect remaining pixels in connected components, and we're doing a little size filtering because we can easily have very small objects that we're not interested in. So we filter all the objects that are too small. And finally, we do a morphological dilatation to remove some remaining holes and add a margin of error for errors. So this is the results on the planar accumulator. So you see that what you've extracted this way are all the individual facets. We have individualized facets. This is the result on the D3 accumulator. So here we have individual foliage, except that as I was saying earlier, it's very difficult to individualize foliage when the foliage is mixing. So often we have one large object consisting of many adjacent trees. If you look at the accumulation of the cylindrical descriptor, you will see the individual trunks. So now we're going to use these different layers to extract individual trees and trunks in the point cloud. So the volumetric layer is going to contain foliage, but it also contains part of the facade. So the solution is that we are going to take as foliage only the part of the volumetric accumulation that is outside the facade. Okay, so this way we're going to remove all the remaining objects that are a bit complex but close to the facade. Okay, and we also have the other problem that the cylindrical layer will contain both trunks and posts. So to solve this problem, we're going to only keep as trunks the vertical linear objects that are inside the foliage, saying that if you don't have foliage around your post, around your vertical structure, it's probably a post and not a tree. Okay, so this is another view of the final accumulation map. So this is the D2 map, the D3 map, D-cylinder map. The last problem we have is that if we have a posts that are surrounded by foliage, we're going to think that they're trees because they are linear structures surrounded by foliage. So to solve this problem, this is where we introduce the laser intensity because posts usually are metallic, whereas trunks are organic and they have quite different intensities in the laser scanner. So we'll differentiate using this. And finally, the last thing we're going to do now that we have the foliage and the trunks is that we're going to associate a unique foliage to each trunk, so we're going to individualize the trees. And this is simply done by associating foliage parts to the nearest trunk. Probably this should be enhanced by doing something like a more intelligent segmentation, but we didn't have too much time to investigate this. So these are the individualized trees in the 2D image, in the 2D accumulation. So you see that we've recovered almost all the trees, but the individualization is a bit brutal. Here you see a view of the same thing when you're going back to 3D. So you're using the accumulation maps to do the tree segmentation, and you see that the individualization is quite well made. But when you have two trees that are adjacent, it's very hard to determine which ones belong to which tree near this separating plane. So now we're going to present a few results because hopefully we had an open data reference over Paris where most of the trees of Paris were positioned very precisely manually. And so using this reference, we could count the number of true positives. And using the number of trees that we have detected and the number of trees in our reference database, we've been able to compute the false positives, false negatives, the correct detection rate, the false detection rate, and the dice. So what we wanted was to have the lowest false detection rate, and maximizing both the dice, which is a quality value, and the correct detection rate. So this is the result. We see that from our database there was 41 trees in our database. We detected 49, so we have a little over detection. The correct detection rate was 80%, so that's quite good. We had only 12 false detection, and the dice value was 83%. So we were pretty satisfied of this algorithm, given that the scene is quite complex. Okay, so now in conclusion, so we have shown that this method has a few limitations, such as it mostly depends on the quality of the data and the scene complexity. Scene complexity, in fact, the most problems we have is when we have occlusions, when we have objects that hide other objects. We can say a lot of things on the objects that are behind, but that's inherent to the type of data acquisition. Probably we could do better if we had a better sampling. Here we had one skyline every 5 centimeters, and for small trees that means that we have sometimes only one skyline on the trunk, so it's a bit limited in order to have a precise trunk detection. We also had a little problem with the geometry of the acquisition. In fact, the acquisition was made more for facade reconstruction than pre-detection, so it scanned only points over 2.5 meters, which means we missed a little bit of the trunks below 2.5 meters. Most of the false alarms we had, in fact, were due to posts that are lying beneath foliage and that have an intensity response close to the response of trunks. So for this, probably we would need image information in order to distinguish them. Also, some trunks were too small and easily missed. And the problem is that these tree detection methods relies entirely on trunk detection. So if you miss the trunk, then you miss the tree. So some of the process need to be improved, but we think it's a good first step towards a good tree detection method based on mobile scanning. And finally, a good point is that using laser intensity allowed to have a good reduction of the false detection rate. That means many posts beneath the foliage were able to be classified using this without impairing the correct detection rate. So our goal was to design a simple and generic methods to detect trees in heterogeneous and complex 3D point clouds. So we've seen that we have quite a good genericity by using only spatial information, so it can be adapted to many contexts. It is highly based on 3D descriptors, and we think that these 3D descriptors that are parameter free because we don't need to have a threshold or a neighborhood size, we think they're very useful. The individual trees were clustered, even if this clustering can be enhanced. It was clustered based on a 2D morphological operations. And the evaluation attests that we have a good detection rate. So it demonstrates the relevance of exploiting local geometric descriptors to analyze complex problem scenes. In the future, we plan on focusing on defining new local geometric descriptors to add to these first descriptors. We would like them also to be parameter-free as our first descriptors. We would like to study how these descriptors may be combined to enhance the detection performance and to improve the geometric descriptors response and improve pole detection. Thank you for your attention, and if you have any questions, I'll be glad to answer.
Thank you very much for the presentation. Well, we have time for questions. Yes, please. That's one question.
Yes, you said you used the entropy to choose from these different scales of here. Why the entropy, or is there a special reason? Why not use just the first best to second best, or the highest value to the second highest? I think that would be more comparable than the entropy.
Well, other things could be chosen. The entropy has the merit of having a sound scientific basis and mathematical basis, and has the exact behavior we want. That means it really favors neighborhoods that have a shape that is close to one of these limit cases. So as the entropy did the job, that's what we chose, and it's really simple to compute. So and it did the job. Thank you.
Stefan?
Can you say something about the computation type of the relaxation technique?
Yeah, the relaxation is the thing that takes the most time because it's iterative and you have to compute things over neighborhoods. I think for 1 million points it was a few minutes for 1 million points, but we did not iterate too much. We did not wait convergence because then at the end, the last iterations, they still take a lot of time to compute and they don't bring a lot of, they don't bring a lot. It converged quite rapidly. So I think we did like maybe 5 or 6 iterations and then we stopped. But it's clearly the most time-consuming step in the algorithm.
Further questions? Are there any questions? Yes, Konrad?
Follow on there directly from Stefan. It takes a few minutes, is interesting, but the question is for wondering how is it implemented? Because I'd be interested, if I use it, could I be expected to get it faster? Can it be parallelized? Or?
Yeah, probably you could make it faster. Well, one of the things that takes a lot of time is to pre-compute all the neighbors you're going to be interested in. And this is not taken into the few minutes. Usually we have some pre-processing where we pre-compute all the neighbors. But this needs only to be done once for the point cloud, and then it's used there are many steps in which we need the neighbors. So these are pre-computed once and for all, and that can take a lot of time because we did quite a naive implementation, but using adequate structures like quadtrees or stuff like that, we could make this much faster. And then probably we didn't spend too much time optimizing the relaxation, and I'm sure that we could have made it much faster. I don't know in detail. The implementation was made by Fabrice, and I don't know exactly how he implemented it. Maybe it can be optimized and brought back down to fewer minutes.
Maybe one last question. Can you say something about the results of the scene? Were there cars present in the scene? You have shown the results, the numerical results. Was it leaf-on, leaf-off situation?
In our context, as I said, we only scanned over 2.5 meters. So we also did that to get rid of this kind of problem. So we don't have cars in our data because cars are smaller than 2.5 meters.
So maybe some trunks are not visible, or is it?
Yeah, that's the problem we had, is that our scanner was too high, so we missed the bottom of the trunks. It will be very interesting when we will have data where we have things below. We'll probably run again things and see if that brings in problems. We are expecting soon a laser that does 360 degrees, so we won't have this problem. The problem is that we have to choose, for each acquisition we do, we have to choose what we're focusing on. And in the team, we were mainly interested either in facets, so we scan above the horizontal, so we're able to go all the way to the top of the facet, or we were interested in the sidewalk, and so we would do 0 degree and below. And for the trees, we would have need to have something intermediate, but it's quite costly. Each time you have to recalibrate everything, and so this was only an internship, and we didn't have we couldn't do one data acquisition, especially for this one.
Thank you very much.
Thank you.
So, our session is scheduled from 4 to 5:30, and I think we have a third presentation which was shifted. Is that correct? Is your presentation already on?